You would have written several programs in higher level language code, compiled them and executed them. In this video, we're going to learn a few more details in this sequence of steps involved in converting higher level language code to a running program. Specifically, we're going to learn about object files, linking and loading. We have looked at this diagram earlier, which illustrates the process of conversion of algorithm to higher level language and then to assembly language and then to machine language, which in turn finally runs on the physical hardware. We are now going to look at a few sub-steps involved in the conversion of assembly language code to a process running on the physical machine. Here is the sequence of steps. The assembly language program gets converted into a sequence of object files, and these object files are linked together to form the executable file. This process is called linking, and then the executable file finally is loaded onto the machine by a process of loading, and after the program is loaded, the instructions are executed in the physical hardware. Often for early programmers, these substeps are hidden because they use an integrated development environment IDE, or they end up using an environment such as the GNU compiler GCC, which acts both as compiler as well as assembler, linker. All of those functionalities are rolled into one. So you miss those steps. But underneath the covers, these are the steps which are happening. In any typical non-trivial program, you usually have more than one file representing the higher level language code, and each of these files gets converted into a separate assembly language code, and in turn each of these assembly language code gets converted into a separate object file. As a specific example, if you have a program split into two C code files, let us say main.c and aux.c, then each of these C files will get converted into assembly language file with a .s extension, and each of these assembly language files will get converted into an object file which typically has an extension .o, and then finally in the linking process all the .o files are combined together to get the executable file. Now, what are some possible reasons why a programmer may want to split up the code into multiple files? Suppose your program overall runs into several tens of thousands of lines. It is unimaginable that all this code will reside in one C file. It is typically split into multiple files and also many times organized across multiple folders. This not only helps in programmability, but also in the fact that if one of the C files is changed, then not all of them need to go through this process of compilation and assembly. So in this example, suppose the programmer modifies something in this file aux.c, then we only need to compile and assemble aux.c into aux.o. This file main.c does not need to be compiled and assembled again. This may not seem like a big deal in this particular examples where there are only two files involved, but if you think of, for example, Linux kernel code which has several hundreds of or even thousands of files, then if only one or a few files are modified, you wouldn't want to compile everything all over again. There is also another advantage to this separation of the steps of compilation, assembly and then linking. You would have used many libraries. Libraries are nothing but pre-compiled and pre-assembled object files. So libraries are reusable pieces of code which are typically already compiled and assembled into libraries. Come with different extension from .o. In Linux, they typically have an extension .so or sometimes .a. It's likely if you have done C programming that you have used this library libmath.a for mathematical functions. Strictly speaking, what an assembler does is take an assembly language file and turn it into an object file. After that, it's the job of the linker. So let's now look at the contents of an object file. One important thing it has is the code or the text segment, and then it also has the data, that is the local variables declared within that particular file, and then it has a relocation table which is a list of unresolved instructions. When you have code split up across multiple files, you will obviously have situations where code in one file calls a function or uses a variable which appears in another file. So this would be unresolved at the time of assembling into an object file. So the object file itself has these unresolved, and relocation table tells the list of such instructions. Likewise, whatever functions and variables are there in the object file, we do not yet know where exactly in memory they are going to be loaded at the time of running. So the symbol table has this information, which is a table of unresolved symbols. Whatever function names and variables which appear within that are yet unresolved. The object file also has a header which describes the object file where each portion of the object file appears, and optionally it could have debugging information. For example, if you have turned on debugging during compilation, this information would also be present. Let's take a specific example to understand object files better. Here we have two assembly language files, main.s and aux.s. Main.s has local variable y, and it has the definition of function main which calls function f. Function f is present in aux.s. There is a reference to variable x which is also present in aux.s. There is definition of function g which refers to local variable y. Let's call these instructions I1, I2 and I3. In aux.s we have local variable x, definition of function f which calls function g which is present in main.s. There is reference to local variable x as well as variable y which is present in the other main.s assembly file. The three relevant instructions I am going to refer to further I have marked here as I4, I5 and I6. So given this, what is going to be present in the relocation table corresponding to main.o? Recall that the relocation table will have a list of instructions which are unresolved at this time. Likewise, what is going to be the contents of the symbol table in main.o? Here is the answer. Relocation table will contain the list of instructions I1, I2 and I3, that is the line numbers or instruction numbers in the text of that object file, and the symbol table will have all of the unresolved functions. Note that at this point all of these symbols are unresolved, both local as well as what is there in the other assembly file, all of them are unresolved. So what this means is that this object file does not yet have valid machine code for the instructions I1, I2 and I3. Likewise, can you now tell what is going to be the relocation table contents in aux.o? Likewise, what is going to be the symbol table contents of aux.o? Relocation table in aux.o is going to refer to instructions I4, I5 and I6 because it is not possible to generate machine code for those instructions, and the symbol table will have the symbols, all of the symbols in aux.s, f, g, x and y. Given the object files, the job of the linker is to generate the executable file. For this, it is going to consider all of the object files and it is going to organize the text as well as data, instructions as well as data in each of these object files as it would appear in memory. I am saying as it would appear in memory because it doesn't actually place the text and data in memory. It is just going to write to an executable file. Once it has determined this piece of text should go here, this piece of text should go in another place and so on, and similarly with respect to the static data, it has enough information to resolve the symbols, and then it is going to use the relocation table to find the list of unresolved instructions, and it is going to rewrite those instructions in the executable file. That is, it is going to generate machine code for those unresolved, thus far unresolved instructions as well. The loader has the job of taking an executable file and actually placing it in memory and running it. So for this, the first step it will take is to place the text and static data in memory, and then before calling main, it has to initialize the stack as well as other registers including argument registers. Now you know that the main function can have arguments, and the argument registers for the main function are actually initialized by the loader. Now who do you think implements the loader functionality? Which entity implements it? Typically, the operating system is the one which implements the loader functionality. Who loads the operating system itself? There is a program called the bootloader which loads the operating system, which in turn loads other programs as determined by the user from time to time. Well, who loads the bootloader? Well, that is hardwired into the machine's booting process. An interesting as well as useful notion is that of dynamic linking. In dynamic linking, the executable file does not have everything it wants linked before it starts executing. It is dynamically determined as to which file must be linked to the exe file as it is executing. Before we see how such dynamic linking is done, can you think of why it is useful to support dynamic linking? There are two main reasons why you might want to support dynamic linking. The first is that if you have dynamic linking, you have smaller executable files because the executable file does not link before it starts executing whatever it needs. So this in turn leads to better use of memory. During execution, only those files which are actually needed for that particular execution are linked. With memory getting larger as well as cheaper, the first reason is not really so strong. There is a subtler reason which is more important for supporting dynamic linking. That is that newer libraries can be used seamlessly. To give an example, suppose you have written a program which uses the math library, and long after you have written the program, the math library undergoes some efficiency improvement. If you use dynamic linking, then your program can get to use the newer library seamlessly. This would not have been possible had you linked your program with the math library at the time you wrote it. Next, let us look at the question of how we can implement dynamic linking. So give it a thought. So you have your program which calls a library function. At the time of compilation, at the time of linking, at the time of static linking, it is not known as to what this function call is. That is, we do not know JAL which destination. So the way this is done is that particular instruction, instead of calling JAL to that function which is desired, it is actually going to call a function which implements the dynamic linking functionality. This dynamic linker can then use a jump table of function pointers in order to determine where to jump. One subtlety to note here is that support of function pointers we cannot do using just the instructions we have looked at so far. We need a new instruction. This goes by the name of JALR or JALR. This stands for jump and link register. So it does jump and link as usual, but the destination of the jump is taken from a register value, which in turn is loaded with the correct value of the function pointer by the dynamic linker. So to summarize, we have looked at how higher level language code goes through compilation followed by assembly, followed by linking and then loading in order to turn into an executing process. We looked at in some detail the contents of object files and how these contents are used in the linking process. And then we also looked at the notion of dynamic linking, which is useful in various contexts.